Okay, here are three more equilibrium type problems. A couple of them are ice table in variety, Q versus K in a variety, and one of them is a Le Chatelier's principle type problem. Pretty standard equilibrium problems. In the first one, we've got carbon tetrachloride being synthesized from carbon disulfide and chlorine. It also makes some S2Cl2. And let's imagine that we've got 1.2 molar CS2. Notice how I'm recognizing that it's 1.2 moles per 1 liter. And 3.6 molar Cl2. Those are my initial conditions. And at equilibrium, the mixture contains 0.9 molar CCl4. So I'm thinking, I see a 3 there, so I'm going to be careful, that the product went from 0 molar to 9 molar. So it's plus 0.9 molar for this product. It'll be minus 0.9 molar for that product. It'll be plus the same 0.9 molar for that product. It'll be minus 2.7 for that, since 3 of those have to go away for each one of those that forms, and it'll be minus 0.9 for that. I could perhaps try to throw that all in my head, but yikes, I better do an ice table, and there it is all laid out. These are the given molarities initially. You never have any product at the initial conditions. And then we did notice that this went to 0.9, therefore it went up by 0.9. This will also go up by 0.9. That'll go down by 2.7 since it has a 3-to-1 ratio, and that'll go down by 0.9 since it's a 1-to-1 ratio. Do your bookkeeping and you have your 4 numbers. It's time to plug in. It'll be this times this over that times the chlorine cubed. Do it. And you'll see that we have an equilibrium constant of 3.33, not bad. Equilibrium constant for the isomerization of glucose to fructose is 0.81 at 25 degrees Celsius. We have some initial concentrations. I notice it's 1 liter, so this is 1.75 molar, 1.25 molar initially, and that's for each of them. Are you at equilibrium? Well, I guess it's just going to be the fructose one, which is 1.25 divided by 1.75. Compare that to 0.81. It's going to be pretty close, but it might be a little low, in which case, no, it's going to shift to the right. So we've answered all that. And then they do want the concentrations when you're done. And for that, let's make sure we do an ice table. Okay, so it is less than 0.81. It's going to shift until it hits 0.81. What does that mean? It means that the glucose will go down by a value of x as it gets consumed. The fructose will go up by a value of x. Not too much, because I think we're pretty close. And that is how things lay out in terms of our equilibriums, which we can plug in. And similar to the last problem, we can solve this for x by cross-multiplying. And there's what x is. And as we predicted, it didn't change much. So why don't we go ahead and subtract that from our 1.75, add that to our 1.25, and we should get 0.81, and the check does show that it does, and so these answer the final question. Those are the equilibrium concentrations of both glucose and fructose. Heating a metal carbonate is necessary to get it to decompose. Barium carbonate will decompose into barium oxide plus carbon dioxide. Now for the equilibrium constant expression, this is not this times this over 0, as sometimes people think. It just means omit solids and liquids. And in fact, that's a solid as well. So regardless, I think it's clear that if you add any reactant, it'll shift it to the right. If you add any product, it'll shift it to the left. So if we add barium carbonate, it will shift it to the right. Adding carbon dioxide should shift it to the left. Adding barium oxide, being a product, should shift it to the left. Heating it, we need to know if it's endothermic or exothermic. So I think the best answer is, oh, look, it says heating it is necessary. So it's endothermic, so sure, heating it should help. And if you reduce the pressure, increase the volume, that reduces the pressure. Well, does pressure help? One thing turns into two. It does not. We want to decrease the pressure, so that should also shift it to the right. That is a few more problems on equilibrium.